So today we are discussing the fundamental solutions of Laplace. He's a French guy, so Laplace and Poisson. Yeah, Poisson too. Poisson too. So Poisson equations. So I recall that the Laplace equation is Laplacian u equals 0. And Poisson is Laplacian u equals f. So yeah, let's say you work on some domain omega, which is an open bounded set included in R, Rn. So those equations appear as stationary solutions of processes like the heat equation, like yeah, concentrations in biology, um, or might sometimes electric fields. Okay, so those equations come from physics again, and they are related to stationary solutions, so things that don't move with time. And so what we saw in the previous lecture is that if I write phi of x as the logarithm of the norm of x, if n equals 2, and norm of 2 minus n if n is greater than 2, then if x is non-zero, then we did the computations and we saw that in fact Laplacian phi equals 0. So functions that satisfy Laplacian phi equals 0 are said to be harmonic functions. All right, and so now today we are trying to find fundamental solutions of the Poisson equations. Okay, that's the question today. And to start with, I propose you an exercise. So you see the problem of this phi is that they are not defined at 0, okay? So there is a singularity at 0. And the first thing to deal with is that well, so we assume that well, let K be a compact in Rn. So we would like to prove that the integral over K of phi of x dx uh, this is finite. All right, so this is an exercise. Try to do it first in the case n equal 2, then in the general case. Right, so we first start with the case n equals 2. And so in this case, our phi of x is the log of the norm of x. And so since we work in R2, I call x and y the two coordinates of my vector. So I have to compute this integral. And so since I work with the radial solution, since the solution is radial, there's a symmetry with respect to 0. I will just use this usual trick, and I will use the polar coordinates. So we did that. You've already seen that. So I just make it so instead of integrating in the ball, which is the disk here in R2, instead I integrate between my angle theta between 0 and 2 pi, and between the radius r between 0 and 1. So then log of the norm of x is just r, and dx dy becomes r dr d theta, right? Okay, so now it's just a simple computation. So first, so nothing depends on theta. So I got 2 pi integral between 0 and 1 of r log of r dr. And this I will use integration by parts. So this gives me minus, I take here an integral of that, indefinite integral of r is r2 divided by 2. And I divided by log of r dr plus uh, I have r2 divided by 2 log of r. All right, so you can see that my singularity has disappeared because at 0, you know that the limit of r log of r is 0. So this term is 0 actually. And it just remains this one. And finally, this. So I will get that finally. Our integral is minus of, right? Yeah. And of course, there's the 2 pi. So finally, I get minus pi divided by 2. So, yeah. So the integral, yeah. So what I wanted to do exactly is that. So that this is finite. Okay. right, so next we are dealing with the case n equals 3. All right, so in the general case, n greater than 2, let's compute the integral over the unit ball of phi of x dx. So in this case, this writes now the idea is to do the same trick, but what we are going to do, so I will say that integrating between 0 over the ball is the same that since I have a radial solution, I will here integrate for the radius r between 0 and 1, and then I will integrate on the boundary of my ball, which is the sphere. So the integral, so now I integrate over the boundary here of my ball of radius r. So r goes from 0 to 1. And so here I'm good, but here what I need to do, so I will take now the function, so I call it y, because y, so y now belongs to the border of the ball. And here I had to take, so it's the Lebesgue measure, but on the boundary. So let's call it S of y. And then I have dr. That's what I do when I do the also in dimension 2. Okay. In dimension 2, the Lebesgue measure here is dsy is r d theta. But here is more general. So now here, since I am on the boundary here, this is nothing but r. So I will take it out. So which means that this is equal to integral between 0 and 1. I took my r outside. And I have here the integral of sy dr. Okay, so but this is nothing but the Lebesgue measure of my boundary. And I know if I work in the dimension n, this is, it's r, sorry, it's r. So this is my Lebesgue measure of the boundary of the ball of radius r. And this is a constant which depends on the dimension. So I call it alpha n times r n minus 1, because the boundary of the ball of radius r is so actually it's an object in dimension n minus 1. And so I have this, okay? Gr, okay, this is a constant, so I can take it out. And finally, this is integral between 0 and 1 of r dr. So finally, I got, this is 1 divided by 2 alpha n. And this is finite. All right. So what we proved, we proved that the integral, and so over any compact k, in fact, of phi of x dx is finite, despite the fact that I have here a singularity at 0. So next we have the following exercise. So assume that U and V are regular, so C2, and defined on the boundary too. So can you compute this quantity and express that as functions on the boundary of omega? That's the exercise. And the hint is to use green formulas. All right, so we just want to compute this thing. So let's do it. So integral over omega of Laplacian u v minus u Laplacian v. So I use the green formula. So this is equal to the integral over omega of, this is basically an integration by parts, but in a higher dimension. So it's grad u grad v, and I have a minus, plus integral, and I will get v grad u, and here I have the external normal derivative, and g, let's say for sigma x. So it's the Lebesgue measure on the boundary. Minus, so I do the same thing. This is symmetric, so I will get the same, is minus integral over omega of grad u grad v dx plus, and this time I got the integral over the boundary of u grad v and the normal. Okay, so this cancels. And so finally, I get that this is equal to the integral of v, and so this, we write it often. For example, we use also mu sometimes. Minus u gv g sigma. Okay. X. Okay, so I have this formula which expresses the values of u and v as a function of the value at their border, at the boundary. Okay. So next, I'm just going to use a slightly different notation for the phi of x. So now phi of x, I just go and normalize. So I want to multiply it by a constant. It will be 1 divided 2 pi when n equals 2 and 1 divided by n, 2 minus n omega n, where omega n is the Lebesgue measure of the ball in Rn. So okay, this is a constant, which depends on the dimension. All right, so that being said, we have the following theorem now. So let u be a function that is C2, then for x in omega, you have that u of x equals. So it will be this formula that I have just used. So there's a sign here that I want to, okay. So equals the integral on the boundary of uy and the partial derivative, the partial normal derivative of phi of x minus y. And so it's dy. I'll put the dy at the end. Minus minus phi x minus y du dn at the point y, and here g sigma y. It's on the boundary. And then I have to add plus integral over omega of Laplacian u. It's not the boundary here, of course. And phi x minus y dy. So I just apply the formula. The idea of this formula is what? I apply the expression that I obtain in the exercise. I apply, where is the exercise? Yeah. So I apply this. But here I replaced, in fact, u by phi and v by u. So here you replace u by phi and v by u. So this term here, you find it here. And here it's here. And the only thing that is different is that now here gives that. Okay. But I recall you that we have a singularity in zero. So that's the point of the theorem. So okay, so I give you 5 minutes. Yeah, look at this equation, reflect on that, and try to identify this with the formula of the previous exercise. All right, so we are going to prove this theorem. And so what's the point? What's the thing is that you can see that it's very close from the formula that we wrote in the exercise. But the problem is that we have a singularity that's our function phi is not defined for y equals x. So phi at 0, it's not defined. So what we are going to do, we are going to apply the formula, but outside of a small ball centered at 0. In this case, everything is well defined. So outside of a ball here of center x and radius epsilon, because the problem is when here y equals x. So I want to take this integral, but I want to avoid y equals x. So I will take this integral, those integrals, but outside of a ball of center x and a radius epsilon. So let's do that. So I will apply the formula. So what I will get is exactly that, but what is what? So I will do the integral, the integral over omega of omega minus a center, a ball center at x and of radius epsilon of. And I will look at Laplacian phi of y minus x or x minus y, and then u of y. Minus, so dy, minus the integral over omega minus px epsilon, and it's phi y minus x, Laplacian u y dy. Okay. So what can you say about that? And what can you say about that? So, but first I apply the formula. And the formula gives me that this is equal to the integral. Okay, but now since we work outside of a ball, I have two boundaries. I have the boundary over omega So this will give me uy and g phi y minus x n minus phi y minus x du dn y g sigma y. But I have also the boundary. Like if my omega is here, I am x here, and I take out a ball here. So I have two boundaries, this one, and now I have also to do the thing with the boundary, the same theorem, but here it's the ball of center x and radius epsilon. And this is the same terms, but it's not at the same place. Okay. And all right, now I need to work. If I look my theorem, I need to work on that. So now next, what we are going to do is take the limit. So take the limit as epsilon goes to 0. So let's do this proof. So what do we have here? So what's the value of this? So the value of this is 0 because phi is an harmonic function. So this integral is 0. This I'm okay because I have it in the formula at the end of the theorem. So I'm going to keep it. So now I'm going to work on all the remaining terms. So for example, this one. So as we see, the integral of phi, so phi is L1 log. So this integral, I can go to x, there's no problem. So as epsilon goes to 0, this will converge to the integral over omega, because this is well defined. I have no problem with that. Okay. So this will converge to the integral of over omega of the same thing. Okay. This I'm okay. I want to keep it. So I need to work on these terms that are remaining here. So I have two. I have two of them. So let's go to the first. Let's work first with this term, but here. So let's look at the integral over the boundary of x epsilon of what I have is phi of x minus y grad u y scalar with ny g, and since I'm in the boundary, the Lebesgue measure of the boundary, on the boundary. Okay. So this takes value in R. So let's look at the absolute value of that. It will be less than the integral over. So y belongs to the to the to the to the boundary of the ball of center x of epsilon. So this means that here, so if you remember the other day, we call phi of something equals this phi, and here it will be epsilon, because the distance between x and y is epsilon, because y it's at the boundary of the ball. Okay. And so this I use Cauchy charts, for example, so I can maximize by the sup of y, but let's say x over omega bar or z or y of grad of u. This is finite because u is of class C2 on omega bar. This is of norm 1, so I'm good. And then I have the g sigma y. All right, but so for example, let's assume that n is greater than 3. What I will get is, so phi of epsilon will be, it's a constant, but phi of epsilon is, for example, so it will be 2 minus n times a constant. This is also a constant, so let's put a constant here and here, but I have the integral of my boundary. So here times that. But this term is, okay, so it's less than a constant of epsilon 2 minus n. And here it's epsilon minus n minus 1, because this is an object of dimension n minus 1. This is the border of the ball. So at the end of the day, I obtain C epsilon. So this goes to 0 when epsilon goes to 0. If I took n equal to, it will be the same, but instead here we'll have, so here n equals 2 gives epsilon, and here it will be log of epsilon, but this also goes to 0. So I'm good. This term here converges to 0. It's not this one, right? It's this one, but here. So you have two terms, one here and one here. This one goes to 0 as epsilon goes to 0. So it remains this one. So this one, but with this boundary. Okay, so let's work on that. Let's work on that. So I'm now considering the integral over my boundary of u y times gradient of phi at y minus x scalar with the normal y dy. All right, let's do this computation in detail. In particular, I have to remind that, so we assume that, so let's do the case n greater than 2. So in this case, phi of y minus x is the norm of y minus x 2 minus n. So if I look, for example, the partial derivative with at the point y minus x, this is y, this is what? This is 2 minus n. So let's do that. So this is yeah. So I just do this computation. I'm looking at the derivative here. So this will be y I minus xy square times 2, and I obtain y1 minus x1. I think I'm good with that. So this will be 2 minus n 2 minus n y1 minus x1 and times 1 divided by the norm of y minus x to the power n. All right. Now I will do the same thing for all the variables so my gradient of phi at y minus x is is 2 minus n divided by y minus x n so it's a vector and it's y minus x. So I just did here. Yeah. Okay, now I have to take the scalar with the normal, but the normal x is here, and I'm looking at the external normal, but it's in this direction. So it's the ball. So here, so when I here, the normal exterior at y is nothing but x minus y divided by x minus y. So if I look at this computation here, things will cancel. And I will obtain, so that grad phi y minus x is actually 2 minus n divided by y. So there's a minus because here I have x minus y and here I have y minus x. So if I do the product scalar of these two vectors, it's minus the square norm of x minus y. But here I have n, so I can just here divided by, take one out, and it's n minus 1. All right, but okay, that's good. But remember that this integral here is on the boundary. So here, actually, this is nothing but epsilon. Okay, so finally, here, so this is not y, but sigma y, because it's not the Lebesgue measure, it's a Lebesgue measure, but on the boundary. And here, I just prove that this is, here, this is minus 2 minus n divided by epsilon to n1. It is. Okay, and so at the end of the day, what remains is, I got that integral over x epsilon of, so I had u y, and I add the gradient of phi at y minus x, scalar the normal at the y, g sigma y. This is equal at integral over the boundary of minus ui. And here, what was that already? It's 2 minus 1 divided by epsilon. 2 minus n d sigma y. So this will be equal to minus 2 minus n epsilon and 1, and integral All right, but this what can I do is just put the value at x. So this will be, let's write it a little bit smaller so that I can finish on this slide. So this will be minus the integral on the border. So I take this out. So minus 2 minus n epsilon n minus 1. And instead, I will take u of x. I forgot here. I have some constant here. I have some constant here. There is a c. There is a c here. There's a c here, and this c is the normalization that I choose for phi. Okay, and so and then I have to. This is new. I put x here. I have y, but here I put x. So I need to add uh, plus 2 minus n, this c epsilon n minus 1 integral over the border x epsilon of ux minus uy. Okay, now since u is regular, this thing will converge to 0. This you can prove that this goes to 0. And this is converging to u of x because u of x, I can take it out. And this constant is chosen, it's the normalization. It's chosen such that this is going to u of x because uh, because because 2 minus 1 divided by epsilon n minus 1 sigma, or constant. In fact, this is equal to the boundary of x epsilon of g sigma y. Okay, that's how we chose the constant here when I took the normalization. So at the end, what I get that this is, so this term here is converging to minus u of x. Okay, so I applied this formula here. So 1 is going to 0. So if I rewrite my formula, let's do it in yellow. Here I will get minus integral over omega of phi y minus x Laplacian u y ui. This doesn't change. And here I will get, at the limit, I will get minus u of x. Okay, so you switch and you get your theorem here. So what do I obtain if u is c infini c infini infinite at compact support in omega. So the boundary vanishes. So in the theorem, where is the theorem? In the theorem, if U is has a compact support included in omega, this vanishes, those term vanishes. So what do I obtain? I obtain U of x equals we obtain that U of x equals Laplacian integral over omega, the Laplacian of U phi x minus y dy. Okay, but in the sense of the distribution, it says that the Dirac at x equals, in fact, the Laplacian of phi in the sense of distribution. So that's why it's called the fundamental solution, because it gives you the solution of the Poisson equation. One F is the Dirac function. Yeah, it's harmonic, but it has a singularity at uh, actually this is phi of x minus y, and you take the Laplacian with respect to y. Yeah, but it has a singularity. So when you take the integral, this is the Dirac. It's harmonic everywhere, but at the center. At the center, it's not harmonic. It's not even defined. Yeah, in zero, but that's why in the formulas, we take phi x minus y. So you transfer your singularity at x. All right, so that's it. That's a nice computations with this singularity, and this gives you the basic tool that will serve to do more other things. So it's used in other things. And in particular, you can find, okay, all the details. Here's some references. So this is Gilbard, Trudinger. For example, chapter 9, for the estimates on LP, it uses these fundamental solutions. And also the chapter on the on the Holder spaces, but I didn't talk about that here. Okay. Yeah. And so historical references for that is the Agmon, Douglas, Nuremberg.